Welcome to clickmyproject.com. We are going to see the product for a computationally efficient reconfigurable FIR filter architecture based on coefficient occurrence probability. Next, we are going to see the abstract for our product. Finite impulse response digital filter is widely used in several digital signal processing applications such as speech processing, loudspeaker equalization, echo cancellation, adaptive noise cancellation, and various communication applications including software-defined radio and so on. Many of these applications require FIR filters of large order to meet the stringent frequency specifications. Very often these filters need to support high sampling rate for high-speed digital communications. The number of multiplications and additions required for each filter output, however, increases linearly with the filter order. Coefficient multiplication is an essential operation in any reconfigurable FIR filter design. The way of its implementation to a large extent determines the design performance in terms of operation frequency, power consumption, silicon area, etc. Common sub-oppression elimination was initially proposed in order to minimize logic resource utilization by removing some redundant sets of the computation, though being specific toward those FIR filters whose coefficients are fixed. The CSE algorithm was further explored and optimized in attempts to improve the efficiency in the use of the logic resources. Complying with the principles of the CSE algorithm, various reconfigurable architectures were also developed. A structure called combination sharing multiplier employs a precomputer to generate some common partial products. Subsequently, multiplication of the coefficients can be carried out simply by performing shift and add operations on those common partial products. A binary CSE method was aimed at reducing the number of those adders actually performing redundant binary common suboperations. Two BCSE architectures discuss, namely constant shifts method and programmable shifts method. The precomputers of these two architectures adapt BCSE method to generate necessary partial products and distribute these generated partial products to each processing element in order to complete. Next, we are going to see the flow diagram for our product. The FIR filter architecture design is proposed. The architecture consists of input data, precomputer, partial products, processing element, output data. The input data is 3 bits. The input data is shifted 2 times right. The precomputer section consists of the input data for the processing elements. The precomputer consists of the 2-bit right shifter, adder and subtractor. The input data is 3 bits. The 3 bits data is right shifted by 2 times. Then the actual input data and the shifted data is full added and full subtracted. The corresponding results are given as output of the partial products. The partial products consist of the actual input data and the full added output result and the full subtracted output result. So actually there are three output of data which contains 3 bits. Then the processing elements consist of multiplexers, programmable shifters, adders, subtractors, and the storage elements. The input data is given to the mux. The mux1 and the mux2 selects the corresponding input data as per our requirement. Both the outputs from the mux is given to the programmable shifters. There are 2 programmable shifters. The mux1 output data is stored in the programmable shifter 1 and the mux2 output data is stored in the programmable shifter 2. Then the output from the programmable shifter 1 and the programmable shifter 2 is full added or full subtracted. Then the output is given to the 2x1 multiplexer and the programmable shifter 2 output is also given to the mux. The max is 2x1. So the system selects either two inputs, either one output from the data. The max 2x1 max selects the one output from the two inputs. The output is given to the full adder. The full adder gets the two inputs of data, one from the 2x1 multiplexer and other from the previous processing element. If the processing element is connected in series, then the previous element output is given as input to the full adder. In case this is denoted as DI, then the corresponding result is given to the max4. Then the max4 result is given as the actual output data. In case of last processing element, the output from the full adder is given as input to the storage unit, and the storage unit output is given to the max4. Then the corresponding output is the actual output. Finally, we are going to see the output for our product. We use the software Xilinx 14.2. Here double click on the FIR code. The software will be opened. The FIR architecture we have implemented is efficient and reduces the computation in the IC. For the new project, click on the file and then create and give the option create new project. Specify the folder to which we have to save our project. Then for the source file, click on the project and give the new source. The program space will be opened. Then add the new source file to our project. For the simulation result, click on simulation and then main and double click on the simulate behavioral model. Double click on the simulate behavioral model. The output will be shown in the iSim. Once the compilation is finished, the iSim will be opened. Here we give the input data to the specified signals and the inputs. Here the input is 3 bits. Then right click and give the force constant value as you decide. Then for the M cell, we have to give the 2 bits to select the desired data. For the clock, we have to give the force clock and leading edge value is 0 and trailing edge value is 1. Period is 1000 nanoseconds. Give the ENN value as 1. FF cell value is also 1. Here the T2 cell value is 0, 1. Then click on run. The output will be shown. Minimize the iSim. For the implementation result, click on implementation and click on the implementation design. Here we can see the synthesis report. The synthesis report specifies the number of LUTs and the flip-flops used in our project, and also the timing report generated. The implementation result is run successfully. Then click on the synthesis report. The synthesis report is HTL synthesis report. Here we can see the number of LUTs and the flip-flops used in our program. Scroll down the bar. Here the number of flip-flops, registers, latches, 3-bit latch, multiplexers used will be shown. Then for the timing generation, click on the timing report. The program delay time will be shown. The program delay time will be in the nanoseconds. Here the data path delay is shown, total 3.195 nanoseconds. For the synthesis report, we have implemented the implementation design. To view the RTL schematic, click on the view RTL schematic, then click on OK, then click on add and then create schematic. The schematic will be created. For the technical diagram, double click on the logic diagram. The desired architecture for our FIR filter has been created. Thank you.